Number 1 says you toss a fair coin 9 times and it lands tails up each time. The probability it will land heads up on the 10th flip is greater than 0.5 or 50%. So basically, are you due for a heads because you've got 9 tails in a row? And the answer is no. If it's a fair coin, the probability is always going to be 50% on each flip, no matter what has happened in the past. Number 2, a random number generator is being used to select an integer in a certain range. What's the probability of selecting an integer outside of that range? And if the generator's only going to select numbers in that range, then you have a 0% probability of getting a number outside of that range. For number 3, we have 11 out of 100 DVRs in an inventory are known to be defective. What's the probability you randomly select a DVR that is not defective? So here we're dealing with the complements of events. You have a 11% chance, 11 out of 100, of getting a defective DVR, which means all the rest of the DVRs have to be non-defective. So that would be 89 out of 100, or an 89% probability of getting a non-defective DVR. For number 4, we randomly select one card from a standard deck of 52 playing cards. Our event, we're calling it event B, is selecting a 5. So how many ways can that occur? And if you're familiar with cards, there are 4 different suits: spades, clubs, diamonds, and hearts. So there are 4 different ways we could get a 5. So event B, selecting a 5, has 4 outcomes. So is event B a simple event? And we're in section 3.1 here. A simple event is an event that has just a single outcome. So this event is not a simple event because there's 4 possible outcomes. If we would have said select the 5 of diamonds, that would be a simple event because there's just one card that is the 5 of diamonds. But getting any 5 has 4 outcomes, so it's not a simple event. For number 5, we're going to use the fundamental counting principle to count the total number of ways something could happen. And in this scenario, we have a lockbox to store keys for a house that's for sale. And the access code consists of 4 digits. And then we have a few restrictions. The first digit cannot be a 4. And the last digit must be even. So what we're trying to count is how many different possible codes there are for this lockbox. And this is covered in section 3.1. The fundamental counting principle allows us to count the total number of ways something like this can be done. And basically what we're going to do is use multiplication and multiply the possibilities we have for each choice along the way. I like to set problems up like this, where I make a box for each decision I'm going to make, and I write how many options I have for that decision. And once you have the numbers for each of those decisions, you multiply them together. And that's the fundamental counting principle. That multiplication result tells you how many total possibilities there are. So notice there are 10 total numbers, 10 total digits, 0 through 9. The first number in this lockbox can be anything but a 4. So what that gives us then is 9 possible things we could plug in for that first number on the lockbox. The next 2 can actually be any digit at all. There's no restrictions. So we have 10 choices for our second number. And we're again going to have 10 choices for our third number. Now our last number on our lockbox has to be even. So there are 5 even numbers: 0, 2, 4, 6, and 8. So we have 5 choices here for the last number on our lockbox. And so multiply these 4 things together, 9 times 10 times 10 times 5, and that gives you the total number of possibilities there are for the code on this lockbox. And the result of that multiplication is 4,500. Number 6, another question where we're trying to count how many ways something can occur. We're going to use the fundamental counting principle. So no questions are left unanswered, and we have a 5-question quiz with 4 multiple choice questions. So there's an A, B, C, and D. There's 4 choices for each multiple choice question. How many ways can we answer that? So to solve this, I've made 5 boxes because there are 5 questions on this quiz, and I need to know how many different options there are for each of these decisions I have to make, each of these questions I'm going to answer. And since they're all 4-choice, multiple choice questions, I have 4 options, A, B, C, or D, for each of these questions. And that's why it emphasized that no question can be left unanswered, because then you would actually have a 5th option of something being blank. But since we're answering them all, we have 4 options for each question, and we're going to multiply 4 together here 5 times and get our result. There are 1,024 ways to answer the quiz. For number 7, we have an experiment where we're rolling a fair 6-sided die, and we're finding the probability of rolling a number greater than 4. And this is from 3.1. It's an example of classical or theoretical probability. It's when each outcome in a sample space is equally likely to occur. In this case, when you roll a fair 6-sided die, you're just as likely to get any of the 6 numbers. And the way you calculate probability in a situation like this, the probability of some event happening is the number of ways that event can occur over the total number of possible outcomes that there are. And that's called the sample space, all the possible outcomes. So for this situation here, the number of outcomes in our event rolling a number greater than 4, there's going to be 2 outcomes. You can either get a 5 or a 6. There are 2 values greater than 4. And the total number of outcomes on a 6-sided die, there are 6 possible outcomes that are equally likely. And so that is the total number of outcomes in our sample space. And 2 out of 6 is the probability. And you can reduce that down to 1/3 or change it to a decimal and round to the correct number of places as a decimal. That would be 0.333. Number 8 is like number 7, where we have classical or theoretical probability. And we are again rolling a 6-sided die, and we're trying to find the probability of rolling a number less than 6. So to find the probability of getting something less than 6, we would put on top of our fraction the number of outcomes that are less than 6, and there's 5 of them. The numbers 1, 2, 3, 4, or 5. And then the total number of possibilities we could get when rolling this dice, there's 6 of them on a 6-sided dice. And so 5, 6 is the probability of getting a number less than 6. And to convert that to a decimal, you do 5 divided by 6 and then round to the correct number of places. Number 9, we have classical or theoretical probability. We have a fair 18-sided die, so each of the 18 sides is equally likely to come up. And we're finding the probability of rolling a number divisible by 5. So to get the probability of that occurring, we need the number of outcomes that are numbers divisible by 5. And so it would be we could get a 5 on the dice, a 10, or a 15. There's 3 ways to get a number divisible by 5. And there's a total of 18 sides on the dice, the numbers 1 through 18. And so there's 18 possible outcomes. The probability of getting a number divisible by 5 would be 3/18. And to get that as a decimal, you would do 3 divided by 18 and then round as needed. Number 10, we have a frequency distribution here, and we're trying to find the probability that a voter chosen at random is in the 18 to 20-year-old range. So this is from section 3.1. This is called empirical or statistical probability. Each outcome is not equally likely to occur, but the probability of outcomes is based upon observations, statistics that we've gathered from probability experiments. And we again have a ratio we set up, and the frequency of an event occurring over the total frequency is how we calculate our probability. The frequency of choosing someone in the 18 to 20-year-old range is 4.4. We can see that from our frequency distribution. And so we have the top part of our ratio here, it would be 4.4. And now to find the bottom part of the ratio, the total frequency, we would need to add up the values from each of the different classes in our frequency distribution. And you can just type those in a calculator. You can copy them into Excel here and use Excel to quickly add them up, but sum those up. And here I'm just going to use the sum of all the different tallies from our frequency distribution, and I get 137.4. And so that would need to be our total frequency down here, 137.4. And if we divide that 4.4 divided by 137.4, we're going to get the probability of our event of choosing someone in the 18-20 years old range. And number 11, we have a scenario that we need to classify as either classical probability, empirical probability, or subjective probability. And these are all discussed in section 3.1. And in our scenario here, according to company records, the probability that a washing machine will need repairs during a 4-year period is 0.05. Now, in classical probability, it's when each outcome is equally likely to occur, like flipping a coin or rolling the dice. That is not the case here. Washing machines are not equally likely to need repairs, as they are not going to need repairs. Empirical or statistical probability is when we actually gather information, observe what's happening, which is what we have. We have company records of what has occurred in the past, and we use those statistics we've gathered to determine the probability of future events off the frequency of how often things occur. So we have empirical probability here because the probability is based off of company records and observations. The third type of probability, subjective probability, is based off of intuition, educated guesses, and estimates. A good example of that is someone trying to give the probability of a certain team winning a sporting event. They're going to use their best intuition, who they think has the better players, how they think they're going to perform, and they're going to state a probability based off of their best educated guess. For number 12, we're going to find the probability using a pie chart here, and it's find the probability that a tulip bulb chosen at random is yellow. So based off this pie chart, we can see the number of different colors of tulip bulbs, and it gives us the number here. There's 35 yellow tulips. So the probability that we randomly select a yellow tulip, there's 35 different ways that can happen, and then we need the total number of tulip bulbs for our total frequency. And we would need to add these three values together, and they come out to 100. And so the bottom part of our ratio is 100, and this is the probability of randomly selecting a yellow tulip. And 35 divided by 100 as a decimal would then give us the probability of 0.35.